chain rules for functions of several variables. What we will look at is first the chain rule for one independent variable, which basically would be calculus 1. And then secondly, we'll look at the chain rule for a function of two independent variables, and then you can always heighten that to a function of three variables, and you can go on if you want with that. Um, this is still the good old-fashioned chain rule. And so first we talk about the chain rule where you have one independent variable. And what we will do here in this section is we can take a problem and they will ask the question, differentiate this function using the chain rule. Basically, what they will say in so many words is use the chain rule from calculus 1. Then they will say, apply the chain rule based on the formula that you're getting in this section right here. Well, you're going to get the same answer anyway, but they want you to look at that in two different ways. Okay? If you have one independent variable, then it stands to reason that you need not go through this complicated formula for one independent variable looking for the derivative with the chain rule. But this formula is exact in that if you have more than one independent variable, we just heighten up this formula, and it applies to function of two independent variables, a function of three independent variables, and so on and so on. So first, let W be a function that depends on two variables. So W is equal to F. It depends on X and Y. Where F is a differentiable function of X and Y, notice that X and Y both depend on T, right? X is G of T and Y is H of T. So T becomes the one independent variable. So what we say here is find the derivative of W with respect to T. Now to get at that, to get at the derivative of W with respect to T, W includes two functions, X and Y, where F is some differentiable function of X and Y. So X becomes a function of T, that is that X depends on T, Y depends on T. W depends on X and Y, so you can kind of go through the chain, and to get the derivative of W with respect to T, you got to go to X. So here the partial W with respect to X, but then within X, X depends on T, right? So here X is equal to G of T times the derivative of X with respect to T. Now W also depends on Y. X and Y both have a T in them, so plus the partial of W with respect to Y. Within Y, there's a T variable, so then the derivative of Y with respect to T. Okay. Now this is beefed up, but you're going to see that this is the same good old-fashioned chain rule from calculus 1. And we'll look at a problem and try to illustrate that. Let's see. Hope you can see that. Can you see that function W? Is that okay? Okay, good. Okay, good. So here, find dW, the derivative of W with respect to T, by using the appropriate chain rule. That's part A. So the appropriate chain rule is the formula that we just got through looking at. And then part B says by converting W to a function of T before differentiating. So part B is basically reflect back on how you took the derivative back in calculus 1. So first part A, I do one, then I give you one to do. So we're looking for dW over dt. This is the partial of W with respect to X, then times the derivative of X with respect to T, then plus the partial of W with respect to y times dy over dt. Here's an interesting question. When you look at this formula, and it's the same one from what we just got through saying, my question to you is, why is there a partial derivative of w with respect to t, but then dx over dt is just a straight derivative? Then the same question is applied here. Why is there a partial of w with respect to y, but then there's just a straight derivative dy over dt? Yes, sir. Exactly. Yep. I couldn't have said it better myself. That's right. That's right. W has more than one variable that it depends on. So you have to do the partials in that. But x only depends on one variable, t. So it's just a straightforward derivative. Very good. Oops. Okay, so we have dw over dt. Take the partial of w with respect to x. That's just 2x, right? And then now the derivative of x with respect to t, that becomes negative sine t. Then it's plus, oh, there's another function operating over there. There's a z. You see that? I didn't see that. So this is plus, watch this. What would this part be over here? The partial of w, times, yes, sir, z, right? Very good. See that? Yep, very good. Yeah. So then this is plus the partial of w with respect to y. We look at w, take its derivative with respect to y, the partial of w with respect to y. So that's just 2y times now dy dt, that's just cosine t. Then plus the partial of w with respect to z, that's 2z. And then times dz over dt, that's times e to the t. Now, to get part B and to get the answer so that both answers look the same, let's take dw over dt and write it as a function of t alone. Because if you think about it now, dw over dt is a function of x, t, y, z, right? But we can write dw with respect to t so that we don't have any more x, y's, and z's in this function. All we want to see is just functions of x. I mean functions of t, excuse me. Well, how to do that? How to get rid of the x, how to get rid of the y, how to get rid of the z? Substitute, exactly. Yep, you got the direct substitution right there. X is equal to cosine t, y is equal to sine t, and z is equal to e to the t. We're going to do that and express that, and then we do part B, and you'll see directly, you get the same answer. So here, dw over dt is, put the negative there in front, negative 2x is cosine t, and that's times sine t, plus 2 times y. Y is sine t times cosine t. Just say cosine t, sine t, plus 2 times z. Z is e to the t times e to the t. That's e to the 2t. Well, the first two terms cancel out, right? Because they're opposites. That's all you have there is just 2 times e to the 2t. Is everybody happy with that? Is that okay? Okay. So now let's do part B. And it says for part B, before you do anything, go ahead and convert w to a function of t first. So we have w, which is x squared plus y squared, but x is cosine t. We're going to square that. Plus y squared, that's sine t squared, plus z squared, that's e to the t, all to be squared. So w is equal to, can I just say 1 plus e to the 2t? So now we find directly dw over dt, where the derivative of 1 is 0, the derivative of e to the 2t is e to the 2t times the derivative of 2t, which is just 2. So this is 2 times e to the 2t. You see how in part A it was good to convert that answer to a function of t so that you can look at both of these, part A and part B, and see, hey, they're both the same answer, right? And they're supposed to be. Again, part B is calculus 1, right? Right. Any questions there? You try this one. Donnie, you have an extra pen? Please forgive me. I did not bring a pen. Oh, I see one up here. Oh, you got one? Okay. I'll just use it. No, I just use this. This is good. Thank you. Crap, I didn't bring my paper. that what you got? You got it, Donnie? Yeah. All right, let's see. So use this chain rule formula. So we're looking for dW over dt. It's the same formula from the previous problem. The partial of W with respect to x times dx over dt plus the partial of W with respect to y times dy over dt plus the partial of W with respect to z times dz over dt. So the partial of W with respect to x is y plus z, parentheses, times the derivative of x with respect to t, that's just 1, plus the partial of W with respect to y. I look for my y's, so I take the derivative, and I have left the coefficients x plus z. Times the derivative of y with respect to t. I look for y, take its derivative with respect to t, that's just 2t, plus the partial of W with respect to z. So I find the z's, and all I have left once I take the partial derivatives there would be their coefficients, x plus y. Then times dz dt, that's just 1. So simplify, this is y plus z plus 2tx plus 2tz plus x plus y. We can write this. This is y plus y, so that's 2y, then plus z plus that x, and then plus the 2tx plus 2tz, and what remains is to replace the x, y, z with what they were up here. X is equal to this, y is that, and z is this guy. So dw over dt is equal to 2 times y, and y is parentheses t squared minus 1 plus z, I think z is just t, plus x, x is t minus 1, plus 2t times x times parentheses t minus 1 plus 2t times z, and z is t. Then we simplify this. 2t squared minus 2 plus 2t minus 1 plus 2t squared minus 2t plus 2t squared. So see there, this is 2t squared, 2t squared, and 2t squared, so that's 6t squared. Got those out the way. And then the 2t minus 2t cancels out. And then all we have left is minus 2 minus 1 is minus 3. And then for part B, you take W and you substitute initially for X, Y, and Z. So W is equal to X, that's T minus 1 times Y, T squared minus 1, plus X, T minus 1 times Z times that T, plus Y, T squared minus 1 times Z times T. Simplify that, so W, FOIL this out, T to the third minus T squared plus 1, and then plus this next term, T squared minus T. I think I was about to write a T squared minus T, and then plus T to the third minus T. So W is 2T to the third. And then let's see, we have that's this guy, that guy. So what about the T squares? They cancel out. And then we have minus T, and minus T, so that's minus 3T, and then plus that 1. Then take the derivative of that. dW over dt. That's just 6T squared minus 3. A little algebra, but you can still get home. Okay. Let's talk about the chain rule, where here the big function W, if you call it that, depends on two independent variables. That is that X, W is a function of X and Y, but X depends on two variables, S and T. Right? X is equal to G of ST. And then Y also depends on two independent variables, S and T, contained or housed within some function H. The same idea in terms of the formula that we looked at, here we just do it more than once. We do the partial of W with respect to S, find that, and then the partial of W with respect to T. So still here the same paradigm, if you will. The partial of W with respect to S is equal to the partial of W with respect to X, because W first consists of a function of F, which depends on X and Y. So those are the two in W that I hit first. Partial of W with respect to X. X depends on S and T, but I'm only hunting for S, right? I'm looking for the partial of W with respect to S. That's all I'm trying to get right now. So this is the partial of W with respect to X times the partial of X with respect to S, plus the partial of W with respect to Y times the partial of Y with respect to S. The same thing here for the partial of W with respect to T. Okay? Let's look at a problem. Here, find the partial of w with respect to s, the partial of w with respect to t, using the appropriate chain rule. Evaluate each partial derivative at the given values of s and t. When we get here, we cannot apply calculus 1. In calculus 1, we only talked about a function that depended on one independent variable. So here we talk about a function that depends on two independent variables, and then you can still heighten that to even more if you wanted to. So we find first the partial of w with respect to s. This is the partial of w with respect to x times the partial of x with respect to s plus the partial of w with respect to y times the partial of y with respect to s. If w consisted of a function of x, y, and z, then you would say plus the partial of w with respect to z times the partial of z with respect to s. So let's see. The partial of w with respect to x, that's just 2x, right? Partial of w with respect to x is just 2x. Then times the partial of x here with respect to s, that's just cosine t. Plus now the partial of w with respect to y, that's minus 2y, times the partial of y with respect to s, that's just sine t. Since w ultimately depends on s and t, we're going to write this partial of w with respect to s as a function of s and t. Somewhat what we did in the previous problem, right? You got rid of x, you got rid of y, you got rid of z, and you wrote that as a function of t. Here, there t was the independent variable. Now s and t are the independent variables. Why do we need that? Because ultimately I want to plug in s equal to 3 and t equal to pi over 4. I don't see that directly where I have that x and I have that y there. So we have 2 times x. X is s. That's cosine times cosines. I'm just going to write cosine squared t minus 2 times y. Y is s, and times the sine t times the sine t, so that becomes sine squared t. Yes, sir. Y is s times sine t, right? Y is s times sine t. X is s times cosine t. That's all. That's all we did. No, you're fine. So this is 2 times s. S is 3 here times cosine of power over 4 to be squared. So cosine of power of 4, that's just 1 over the square root of 2, or square root of 2 over 2. So this is, let's say, 1 over the square root of 2 to be squared, minus 2 times 3 times sine of power of 4 is, again, 1 over the square root of 2. That's to be squared. You get 0. Now let's see what happens when we find the partial of w with respect to t. The partial of w with respect to t. The formula is the partial of w with respect to x times the partial of x with respect to t plus the partial of w with respect to y times the partial of y with respect to t. So the partial of w with respect to x, again, that's 2x, times the partial of x with respect to t, that becomes negative s sine t. Negative s sine t. And then this is plus the partial of w with respect to y, that's minus 2y times the partial of y with respect to t. That becomes s times cosine t. So this partial of w with respect to t. We clean that up. That's 2, or negative 2 x was that s sine t, right? X is s, excuse me, cosine t. X is s cosine t. This is s cosine t, and then times this s sine t. A lot of s's in there. Minus 2s times y. Y is s sine t. S sine t times that s here, cosine t. 1, 2, 3 s's. 1, 2. First, I'm missing an s somewhere. Let's see. This is negative 2 times x. X is s cosine t. One, two, three. 3 s's over here, 2 s's over there. So again, this is negative 2, and then x is s cosine t times that s times the sine t. Okay, we got that one. Move over here. This is negative 2 times, and y has, I think I added in an extra x, yeah, extra s. Yeah, so this is negative 2, y is s sine t, then times this s cosine t. Yeah, it's just s squared. Gotcha. So this gives us negative 2 s squared cosine t sine t minus 2 s squared cosine t sine t. Now you can factor out a negative 2s squared if you want to. I mean, that's fine. I'm just going to leave it just the way it is. Negative 2 s squared. Cosine is 1 over the square root of 2. And then sine t is power 4. 1 over the square root of 2. Pardon me? No. No. If it was negative and positive, they would. Right. Oh yeah, I forgot. S is what, 3? Yeah. So this is negative 2 times 3 squared, 1 over the square root of 2 times 1 over the square root of 2. So the two radicals multiplied is 1/2 times that negative 2. We just get negative 9. And then over here we get negative 9. Negative 18. Okay. All right. I'm going to give you one. I won't do it, but I'll just write the answer. But I want you to see if you can work this one out. Yes, sir. S equal 1, T equal to 3. Got it. Good. Everybody good? Get 4 for the first one and 12 for the second one. Let me give you one more. Wait. Okay. Okay. Now I believe you. If you got 4, then everybody good? Okay. Any questions there? Let's talk here. The last um, part of this section deals with implicit differentiation. Implicit differentiation. You recall from calculus 1 when you would look for the derivative implicitly, it was to imply that the variable that you were looking for also depended upon another variable itself. And so we talked then in Calculus 1 about uh, finding the derivative implicitly because some functions may be written out in a way that is difficult to isolate a variable by itself. And so, do you remember that from Calculus 1? So recall, find the derivative for, let's say y equals the square root of 4 minus x squared. So you said that this was y prime is equal to 1/2 times parentheses 4 minus x squared raised to the negative 1/2 power times the derivative of the inside. That just gave you minus 2x. And so you said that this was negative x over the square root of 4 minus x squared. Here, y is explicitly expressed as a function of x. Y is explicitly expressed. That is, y is isolated. Right? Here, y is explicitly expressed as a function of x. But what if we want to find the derivative of y implicitly? Okay. Take the equation above where y is implicitly expressed. That is, if we have x squared plus y squared is equal to 4. So here we say take the derivative of y implicitly. So here find the derivative of y implicitly. In other words, don't isolate y. Just leave y within the equation. So here we take this derivative. This implies that we have the derivative of the x is 2x times its derivative dx over dx plus 2y times the derivative of y as dy over dx. Here y depends on x, so then is equal to the derivative of 4 is 0. So this implies that we have divide through by 2, so we have x plus y times dy over dx is equal to 0. Now we isolate dy over dx. So that gives us first y times dy over dx is equal to negative x. And this implies that dy over dx is equal to negative x over y. but y is equal to the square root of 4 minus x squared. Right? Y is equal to the square root of 4 minus x squared. So here this is negative x all over the square root of 4 minus x squared. Now here you found the derivative of y implicitly, right? And we got this. And then up here we found the derivative of y explicitly. You get the same thing. Now do you recall that from Calculus 1? So you can talk about a function where, say for example, y is expressed here explicitly. So y is by itself, it's equal to something. Take that derivative. But sometimes y may not be expressed so easily. It may be encoded within a function, and it may be difficult to get the y variable or whatever variable you're looking for the derivative by itself. So if that be the case, then we find the so-called derivative or partial derivative implicitly. Yeah. So that's the idea here. What if the function depends on several variables? Well, that's why we talk about, in this section, find the derivative implicitly, where you have a function that depends on more than one variable. So the argument is this. Let w be a function of x and y. Let's say, for example, here we set this function equal to 0. Now, they do that, and it's a real neat trick by getting this function w to equal to 0. W is actually a function, say, for example, you have this function f of xy that's actually equal to some number. Like you have some functions of, some terms of x and y is equal to, let's say, 10. So now what they do is they subtract 10 on both sides, so leaving 0 on that right side, and they call that w. That's all they're doing. We'll talk about that later, I believe in chapter 15. So now what we want to do is to find the derivative of w, dw, here over dx. Notice here that y is equal to little f of x. So the ultimate independent variable is x. So this becomes the partial of f with respect to x times, when I go inside of here, of x, and look for its derivative with respect to x, that's dx over dx, plus the partial of f with respect to y. Yes, sir. Yes, sir. Times, I go inside of y and I find its derivative with respect to x, dy over dx. This is equal to 0. So I want to get dy over dx by itself, the same argument that I just did up here. Right? Same argument up here. So I'm trying to isolate this term right here. That's what I want by itself. So I have the partial of f with respect to y times x of xy, excuse me, times dy over dx is equal to negative. Now notice that this guy right here is just 1, right? That fraction, that ratio there is just 1. So this is equal to minus the partial of f with respect to x of xy. So this implies that dy over dx is equal to negative the partial of f with respect to x of xy over the partial of f with respect to y, xy. Now, the theorem for the implicit differentiation is based off of this proof right here. So everything else that you're looking for will look just like this. Let me show you. If w equals to f of x, y, z, I don't know if there it is. Yep. Then the partial of z with respect to x. Here's what I'm getting at. Let me show you the trick. If I'm looking for dy over dx, right, looking for dy over dx, then this is always equal to a negative ratio of the partial derivatives. Now, what would these partial derivatives be? This is how I keep it in my head. If this is dy up here, downstairs is the partial of f with respect to y. If this is dx here, upstairs the partial of f with respect to x. It works like that for every last one of them. Let me show you. So here the partial of z with respect to x, this is negative capital F sub x of x, y, z all over capital F sub z of x, y, z. You see that? If you want to find the partial of z with respect to y, negative capital downstairs is the partial with respect to y, upstairs over here is the partial of f with respect to y of x, y, z all over capital upstairs is the partial with respect to z. This is capital F sub z of x, y, z. Now, this is what he is explaining in the theorem right here. I didn't note that in my explanation, but this is very important, that the partial of f with respect to z is non-zero. Why is that the case? It's the denominator. Well, good. Let's look at some problems. Here, differentiate implicitly to find the first partial derivatives of z. Here, z depends on x and y. I'm looking at this function as x, y, and z. So you want to find the partial of z with respect to x. Let's write the formula. This is negative f sub x of x, y, z all over capital F sub z of x, y, z. And you want to find the partial of z with respect to y. This is negative capital F sub y of x, y, z all over capital F sub z of x, y, z. All right. Three things that I want to find separately. I want to find the partial of f with respect to x of x, y, z. Find that. Find the partial of f with respect to y of x, y, z. Should be just parentheses. then find the partial of z, x, y, and z. Okay. So I look at this guy right here. I find its partial, and you ask the question, what is this is really a function w. See that equal to 8 over there? So it's not necessarily equal to 0, right? As what was stated, initially. Here, this is basically the left side minus 8 equal to 0, and then you get w. So here we've just found the partial of f with respect to x. So this is the derivative of the x is 1 times its coefficient, natural log of y. There's no more x's there, so that's it. Find the partial of f with respect to y. Well, here, that becomes the natural log of y, take its derivative as 1 over y times the derivative of y. That's just 1 times the x. So this is just x over y. Plus, I have another y there. That's y squared times z. So that's plus 2yz. Now find the partial of f with respect to z. So that becomes y squared plus 2z. And everything else is just as simple. Just plug in this information into the ratios and you get your answer. So the partial of z with respect to x, using this formula right here, is negative f sub x up top. That's the natural log of y over f sub z. And we got there y squared plus 2z. That's it for that one. The partial of z with respect to y is a negative based on the formula. Upstairs is f sub y. Well, this is x over y plus 2yz all over f sub z. That's y squared plus 2z. You can simplify that because there's too much going on there for that second one. So the partial of z with respect to y, that negative is sitting out in front. This is x over y plus 2y squared z over y divided by y squared plus 2z. This becomes negative x plus 2 y squared z all over y to the third plus 2 yz. Always wondered back in the, I don't know, 8th grade, where were those complex fractions going? I don't know if y'all remember that, like, oh man, 2 over 3 minus 6 over 7 over 1 plus 4 over 5. Y'all remember that? Yeah. Oh boy. Okay. Okay, your turn. was the easy one, right? Yeah. Okay. Let's see. Got partial of z with respect to x is negative x over y plus z. Everybody good to go on that one? And the partial of z with respect to y is negative z over y plus z. They all had a factor of 2 in them. You just divide that 2 out and that goes away. No, it's still right. Yes, sir. No, it's fine. Yep. Even, let me go back. Like if you wrote this for your answer, obviously I'll mark it right. You know, it's still right. I just simplified down here and got this guy. So differentiate implicitly to find the first partial derivatives of w. So here w depends on x, y, and z. So we'll do this one, and I think I had one more, but I think if you get it, then we can take a break. So here, find those partial derivatives, partial of f with respect to x. Just use my shorthand. It's just 7y. Any more x's there? There's one with that w squared, so this is plus w squared. Find the partial of f with respect to y, not x again. That's 7x plus z squared. Any more y's? I think that's all the y's that I see. The wise old owl sat on an oak. The more he heard, the less he spoke. The less he spoke, the more he heard. How come we can't be like that wise old bird? I don't know, 9th, 10th grade English class, Miss Taylor. She didn't like us, but anyway, sir. I hope she. No, I don't know. I'm just teasing. Man, she was old because she was like then. Yeah, she was like my mama's teacher. You know. Yeah. So she's gone. Man, she was rough. She was rough on us. And then I had this one teacher in middle school. She was my uncle's teacher, and my uncle, she said, was bad. And so she just made the assumption that I was bad too. And I mean, I wasn't. I was like a quiet little fella, you know, and wouldn't say anything. And so if it came down to a question of grades, and they did stuff kind of strange back then in school because they'd have 2 students go up to the board and do a presentation, and then the teacher would say, okay, I'm going to give you a 80, and then, okay, I'm going to give you a 40. And so if it was me, just because it was me, you know, I'm getting a 40. I'm like, why? I know your folks. What does that have to do with anything? No, so, yeah, in high school. And so that was like, you know, first 9 weeks she was rough on me. Second 9 weeks she gave it to me. And I would talk to her, I said, Miss Taylor, I said, please, can you grade me based on my performance in this class and not anything to do with, you know, my uncle? And she was like, it's just in your blood, Williams. I said, Miss Taylor, come on. Yeah, I mean, these teachers were rough back then, man. So I prayed about it. You know, I said, Lord, you got to, touch her. Not kill her. Not kill her. I just said, Lord, please touch her heart. And so the last 9 weeks, she finally came around and she started grading me based on what I was doing in the class. And she apologized. She said, Williams, I'm sorry. So I made a wrong assumption based on your uncle and your performance here in this class. I said, well, thank you, Miss Taylor. I'm glad you came to that realization. And so my grade, the last 9 weeks of my class was a whole lot better than. Well, but you know what? The Lord fixed it all. So, yeah. So, but yeah, that was something. But her name was Miss Taylor too, so she was the fat Miss Taylor. That's what we called her. Anyway, but we had one was the fat Miss Taylor, the other was the old Miss Taylor. So the old Miss Taylor was in high school. The wise old owl sat on the oak the more. Yeah. What you say she's gone? So anyway, the partial of f with respect to z. There's a z there, so that's 2yz minus 4w, and then plus w squared. Then the partial of f with respect to w, negative 4z, I'm looking here, and then plus 2wz plus 2wx. So the partial of w with respect to x is negative f sub x of x, y, z all over the partial of w with respect to x, y, z. So this is negative f sub x, that's 7y plus w squared over f sub w. That's a long one there. Negative 4z plus 2wz plus 2wx. Now, you can hide that negative if you wanted to. You can leave it the way it is, but those two negatives out in front, it's kind of misleading. So 7y plus w squared. I'm going to factor out a negative downstairs and then divide it. Negative divided by negative goes out. So this is just 4z minus 2wz minus 2wx. Partial of w with respect to y, just negative f sub y of x, y, z over f sub w. Yes, sir, of x, y, z. Mm-hmm. I factor out a negative from downstairs. So it's negative divided by negative. So if I factor out a negative from downstairs, that leaves me positive, negative, negative. You don't see it, do you? Yes, sir. It's just a negative in front of that 4z. Yeah, 4z is only, right, negated, not the 2wx and the 2wz. Okay, yes, sir. So this is negative out in front, and then this is f sub y, that's 7x plus z squared all over at negative 4z plus 2w wz plus 2wx. Do the same thing with the negatives on that one. So this is 7x plus z squared over 4z minus 2wz minus 2wx. And then the partial of w with respect to z is negative f sub z of x, y, z all over f sub w of x, y, z. And f sub z, get the negative out front, this is 2yz minus 4w plus w squared all over f sub w, negative 4z plus 2wz plus 2wx. And so, again, I'm going to factor out a negative from downstairs, and then negative divided by negative will go out. So this is 2yz minus 4w plus w squared all over 4z minus 2wz minus 2wx. Any questions with those? Okay. Well, I think we got it. Let's take a 5-minute break, and then we'll come back and talk about the test for tomorrow.